who will tell us about connected McMullen-like Julia sets via singular perturbations. Jordi.
Is it better now? Okay. So as I was saying, the goal of today is to understand the relation of these two drawings of these two Julia sets. To the right, as I was saying, we have a Cantor set of quasicircles coming from McMullen's singular perturbation. And then to the left, we have the Julia set of a certain parameter for what's called the Chebyshev-Halley family of root finding algorithms. So that's a sketch of the talk. So I'm going to be talking about first, I will recall for those of you who don't know about singular perturbations, and I will recall the very basics from McMullen's family. Then I will talk about the Chebyshev-Halley family of root finding algorithms, and then I will go and see how those can be studied from the point of view of singular perturbations. So can we really hide this bit in the bottom because the references are being hidden? It was. Maybe. Task cover view off. Off. No, no help. No. So doesn't matter. No problem. Okay, so anyway, so let's continue this. So sorry, you cannot see I guess you can see the references from home, but not here. So singular perturbations were introduced by McMullen. He studied the family sets where, okay, he studied this family set square plus lambda over set cube to show the existence of varied Julia components which do not lie on the boundary of any Fatou component. So what's the idea? The idea here is that you start with set squared. So you start with set square, you have the dynamics, you have 0, which is a super attracting fixed point, and all the dynamics go in, or all the things tend to 0. You have the basin of attraction of 0, which is the unit disk. And then you add a singular perturbation. So you add a term which is plus lambda over set cube. So you are adding a pole at 0. Whenever you are adding a pole at 0, what happens is that the points they are still remembering that they want to converge to 0. So whenever you look at the Julia set, so what you see is that the points first they go in. But at some moment, whenever they reach a certain annulus, they say, come on, but there is a pole. So whenever you are close to 0, points try to go out. So this is how you have this kind of dynamics that you're going in, you're going out, okay? But still, I'm not going to talk about much this. So then this family was studied in a more general setting in the case set to the power of d plus lambda over set to the power of n by Devani, Luke, and Uminsky. And They studied several general properties of this family. They studied very well the dynamical plane, and this family has certain features which are important, such as Z equal to 0 is the unique pole, infinity is still super attracting, and they have, it's important, they have n plus d free critical points, which are given by a certain formula, which is not important, but what's relevant is that the n plus d critical orbits are symmetric. You have n plus d free critical points, but you do not have n plus d free critical orbits. There is a single free critical orbit, okay? Because you have symmetry by n plus these roots of the unity, which ties their dynamics. Okay, I don't know if there's. So one of the main results from Devani, Luka, Numinsky is what's so-called the escape trichotomy. This escape trichotomy states that whenever all free critical orbits of these maps converge to infinity, then the Julia set is either a Cantor set, which is the left case, or a Sierpinski carpet. Sierpinski carpet is a homeomorphic image or of a Sierpinski curve, or it's a Cantor set of quasicircles which separate 0 from infinity. Okay, and this is the setting, and I don't know what happened here. Okay, so now we go now to the family we want to study, is the Chebyshev-Halley family. The Chebyshev-Halley family, these rational maps I want to study, they are obtained by applying the Chebyshev-Halley methods to the algorithm set cube minus 1. If you are interested in what's the formula for these Chebyshev-Halley methods, you can find it in Dan's posters downstairs. This is a family of methods. Every parameter represents a different numerical method. This family contains several known methods, such as Halley method and Chebyshev method, for instance. And this is a family of methods which have order of convergence 3 to the roots. So if all the roots are simple, if the root of a root of a function is simple, then you know that you will have order of convergence 3 to that root. In particular, if you apply it to set cube minus 1, you will have that the third roots of the unity will be super attracting fixed points of local degree 3. And we can see, for instance, here some of the Julia sets of this family. To the left, it would almost seem like we have Newton here. So what happens is when A tends to infinity, when the parameter tends to infinity, these methods actually converge to Newton's method. And if you look close enough, you will see, for instance, here, there's a hole. Okay, so one of the things that Dan's explaining on his poster is that actually you can get rid, if A is big enough, you can get rid of of these holes. And you can show that in the main component, this is the dynamics are conjugate to the dynamics of Newton map. Okay, but this is not the topic of today. But what I want to notice here is, so I want to notice here that, as I said, we have 1, 2, and 3 roots of the unity, which are super attracting fixed points. You have here to the left, but we have here the same to the right. Very, very different feature from these root finding algorithms with respect to Newton, for instance, is that infinity can be attracting. So in this right figure, what we see is the black region is the basin of attraction of infinity. Okay, so in some sense, those are not numerically as well, do not behave as well as Newton. You get greater order of convergence, but you pay it with worse global dynamics, so to say. But another.
Sorry, Jordi, could you go back to the slide very quickly of the definition of the family?
Mm-hmm.
So you've got just one complex parameter.
I got what? Yeah.
And you've got a degree 6.
Degree 6.
Rational map. So you have 10.
You have 10. I'm going to go.
Okay.
To that.
Okay. All right. Thanks.
But now that I'm coming here, I can go to what I was talking about Newton. If you check the family, you can see that the numerator is degree 6, the denominator is degree 5, but which means infinity is an attracting fixed point. But somehow this parameter a in front is telling you which is the multiplier at infinity. So the multiplier is essentially, it's not exactly, but it's essentially of the order 1 over 2a. So this is the kind of things that you can still make this attracting and even super attracting in some degeneracy cases. Okay, so what's another important feature is that you can see here, it's easier to explain this over the drawings. That if I do like this, if I get angle third, you can see a copy of everything all time. So if I go here again, angle third, so you have actually a symmetry. So in this case, we have these maps are very symmetric. So one of the reasons we keep having that many parameters A is in order to ensure that we are keeping the symmetry. Because as Lasse was saying, we have 10 critical points, but we do not want to deal with that many free critical orbits. But we are only going to have one free critical orbit. So that's an important thing to keep in mind. So, and that's actually what's saying here, that we have degree 3. The dynamics are symmetric with respect to rotation by the third root of the unity. Okay. Okay. And now Lasse was asking about critical points. Here we are. So we have degree 6. We have 10 free critical points. We have super attracting the roots of the unity, which are super attracting fixed points of local degree 3. This already gives us 6 critical points. Okay, if we look here, we have a term which is z squared in the denominator, which means 0 is a double preimage of infinity, which implies 0 is a simple critical point. So we have already 7 critical points whose dynamics is prescribed. So those are not free at all. And then we have 3 extra critical points, which are given by this formula. You don't need to check this, but the only important thing here is that they depend on a third root of the unity. So they are symmetric with respect to rotation by a third root of the unity. And since the dynamics of the map is symmetric with respect to third root of the unity, what we are going to have is a unique critical family in the sense that we only have one free critical orbit. Okay. Another important feature of this family is that we can actually study easily, more or less easily, the connectivity of the Julia set. Okay. There is a characterization. I'm here just putting some simplified version, which is what I need, but you do get an easy characterization of when the dynamics is connected. The first reason is that you can prove that there are no Hermann rings. So there is a small trick. If you are symmetric with respect to rotation by third root of the unity, you can always semi-conjugate by the map set cube with another map, where essentially you are going to collapse all free critical points. So you are going to be this family semi-conjugate to another family which essentially only has one free critical point, but literally one free critical point. No symmetries there. So so there is only one critical orbit and no symmetries there. So that semi-conjugate family cannot have Hermann rings. So you get from there that this family cannot have Hermann rings. So essentially what happens is whenever you want to study connectivity of this family, you only have to take care of basins of attraction, essentially on parabolics. Okay, because there are simply, you cannot get, so to say, enough critical points to create holes in preimages. Since there is only one critical orbit, it's essentially, and you need, in order to get two, in order to have the Fatou component, a preimage of a simply connected Fatou component to be multiply connected, you need more than one free critical point. So somehow you can use that to prove that if modulus of A is small enough, the Julia set is connected because the immediate basin of attraction of the roots cannot contain any free critical point. Okay, so now we go to the singular perturbation. So if you remember, I was saying that you usually have something like z to the 4, and you add, or z square, and you add plus lambda over z to the cube. That's not what we are doing in this case. So we are starting from a family, and we won't study it from the point of view of singular perturbations. So what we do is we start with this family, our original family, and we go and say, well, we want to understand the parameter plane of this family. And the first thing that we want to know is this actually a degree 6 family? Well, not exactly. This family has degeneracy parameters. You have parameters for which the degree drops. And when the degree drops, you are going to be in the bifurcation locus, and you want to know what's happening, what's going on. And here, the most interesting parameter is a equal to 0. Okay, if you check the formula from, that you can find in Dan's poster, it's going to depend on alpha, not on a. This is just a reparameterization so that the degeneracy parameter is at 0. So and if you take a equal to 0, you can see here that this term disappears. The denominator drops the degree, the numerator drops the degree. It's now degree 5, degree 3. The denominator is still degree 5. So we pass from degree 6 to now this has degree 5, degree 5. So we've dropped in 1 the degree. So now we need to understand, well, what's the dynamics? Once you have the degeneracy parameter, you need to start by studying what's the degenerate family, so to say, the degenerate rational map. So what happens now? Now notice that the degree of the numerator is 3, the degree of the denominator is 5. This means that infinity is mapped onto 0 now. Before, infinity was a fixed point. Now infinity is mapped onto 0, and is mapped onto 0 with degree 2, because the degree of the numerator is 3, the degree of the denominator is 5. So the infinity is mapped onto 0 with degree 2. So now 0, infinity form a period 2 superattracting cycle. So before infinity was a fixed point, now infinity forms a superattracting fixed point, superattracting period 2 cycle with 0. And what's important also, so in this case, we are going to be interested in how are the dynamics near 0 somehow. So we are always going to be considered the map R squared. So it's not having period 2, having singular perturbations when you have period 2 is not that easy. So the first thing you do is, well, let's take the square of the map. We take the second iterate of the map. Now we have a superattracting fixed point at 0, a superattracting fixed point at infinity, both of them of local degree 4. And this map, by the way, does not have any free critical points. The critical points are the roots of the unity, 0 and infinity. So that's how the dynamical plane looks like. So we have here 0 is here, we have infinity somewhere here, and we have here a period 2 superattracting cycle. Okay, and by the way, everything looks nice because all photo components are bounded by quasicircles. Everything's hyperbolic, everything's very nice in here. Okay, and now we want to understand this from the point of view of singular perturbations. And if I have the idea basically is that I add a simple pole at infinity. When I take a different from 0, I add a simple pole at infinity. If I have a rational map and I want to add a simple pole at infinity, the only thing I need to do is I add lambda set. If you add lambda set and infinity is not a fixed point, after you add lambda set, infinity is a fixed point. Okay, but the problem is if I add lambda set, this will not preserve any kind of symmetry. So that's why we consider this singular perturbation with that many parameters. So somehow this is the way of adding the simple pole at infinity while keeping all the symmetries in the dynamical plane, so that allow us to work correctly and to be able to do surgery and to be able to know where are we going to finish. So now we want to focus, as I was saying, in the dynamics of R squared. So if I consider R squared for A equal to 0, Z equal to 0 is a subtracting fixed point of local degree 4. And if in particular Z equal to 0 is a double preimage of infinity, it's always, so I'm not touching the dynamics. Whenever I add the singular perturbation, I'm not touching the dynamics at 0. 0 is always a double preimage of infinity. If I add a simple pole at infinity, what's going to happen is that for R squared, first for the first iterate, 0 is mapped with degree 2 to infinity. The second iterate, there's a simple pole at infinity. Infinity is a fixed point, simple fixed point. So 0 is mapped with degree 2 onto infinity for R's for the second iterate of R. So before perturbation, we had Z something of local degree 4. So we had Z to the power of 4. After perturbation, we have a double pole at 0. So locally, what's going on is that the map behaves around near 0. Our map looks like Z to the power of 4 plus lambda over Z squared. So locally, that's what happened. Before perturbation, we have Z to the power of 4. After perturbation, we have lambda over Z squared. And that's what we actually want to justify. What we want to justify is that we can actually see the dynamics. If lambda is small enough, we can see the dynamics of this map in the Julia set. And up to where can we see the dynamics of this map in the Julia set? But I have not shown yet any figure of the parameter plane. So to the left, we have the parameter plane near A equal to 0 for the Chebyshev-Halley family. To the right, we have the parameter plane of the map Z to the power of 4 plus lambda Z squared. Okay, and you can see they look very, very much alike. So what I'm going to present is a surgery which actually is going to be valid. I'm going to say at some moments A is small enough, but what's going to happen is that the surgery is built to actually, it can be shown, but it's built so that it actually be working in a neighborhood of this fold parameter plane. So usually whenever you do singular perturbations which are not respecting this symmetry, which are not of this form, you end up getting results of the form if modulus of A is small enough, is modulus of A is small enough. We are going to get the results which actually work in the full copy of the parameter plane that we have here. Okay, so which kind of things do we see? You've already seen this figure. This is the kind of figure that you will see for A small enough. For A small enough, you see the Cantor set of quasicircles. And you see here how everything seems to be connected. As I mentioned, if A is small enough, the Julia set is connected. What's happened here is that the critical points actually belong here in preimages of the immediate basin of attraction of the roots. If the critical points do not belong to the immediate basin of attractions of the roots, the Julia set is connected. So what we see here is an invariant Cantor set of quasicircles within a connected Julia set. And actually within a locally connected Julia set. So this is here to the left, it's a locally connected Julia set. The dynamics here are hyperbolic. And to the right, we see the Cantor set of quasicircles of McMullen. But can we have other things? Can we have the Sierpinski carpet? Yes, we can. Here you have a copy of the Sierpinski carpet in the Julia set. And you would go and say, okay, Sierpinski carpet, not, okay, it looks nice, but we had also the Cantor set of points. We can actually also even see the Cantor set of points here that is inside invariant. The Cantor set of points coming from McMullen is still appearing clear. You can see it more or less. I don't know how well can you see it from the back, but it's still here invariant. You can see it in the dynamics of the map. Okay, it's green, yes. So in the end, I have some time, so I will be spending some time on trying to get the ideas of the proof. Okay, so the main result that we prove is that, okay, oh, sorry, can I move this? No. If modulus of A is if A is in the set lambda, I have not defined the set lambda, but essentially it's going to be a neighborhood of where you see the copy of the parameter plane of the family. If modulus of A, if A is in lambda, then there is a doubly connected set such that there exists a quasi-conformal conjugation of the map R squared. So we have the map R squared is going to be semi-conjugate map, a certain quasi-conformal map phi with a McMullen map of the form Z4 plus lambda over Z squared. Okay, for sure, this semi-conjugacy, this conjugacy is only going to be valid as long as the iterate dynamics do not exit this annulus. So in the end, this conjugacy is only going to be valid on the Julia set, which is invariant by this map. And notice again that we are having the conjugacy, we are having it with R squared. Okay, we are not having it with R because you have this thing of I first go to infinity and then I come back and I look at things near zero because it's usually simpler. And then what's more important is, well, but how much of the dynamics of the McMullen map are actually captured by this conjugacy? So the result, the main part of the result is actually that the preimage by the conjugacy map of the Julia set of McMullen map is actually in this annulus. So we will see in this annulus where we are doing this, the surgery, we are going to be watching all of the Julia set of McMullen map. Okay. So up to here, is any question? Is the result clear, more or less? Okay, tell me.
Sorry, you might be coming to this later on, in which case just tell me to shut up. But are you saying that? So when you are in this annulus, if you just look at the set of points that stay forever inside this annulus,
yes.
Do you get a conjugacy between the dynamics?
Yes.
Okay, thank you.
So actually, how do you do this? So what do you do? So the first thing, the idea is to do some sort of the surgery like the strengthening map, the strengthening theorem for polynomial-like mapping. So we are going to do something. If you want to think of this, you have to think of the strengthening theorem. So we want to build some sort of polynomial-like map situation. So let's say a McMullen-like map situation, so to say. So how do we do that? So what I'm going to prove is that we can get this kind of configuration. And this kind of configuration is the following. I'm having the annulus where I'm going to have the conjugacy is the yellow annulus. So what I'm going to show is that first, just remember, by the way, that for polynomial-like mappings, what do you have? So I have one set U, one set V, I have U, I have V, I have a map which is proper with degree D greater or equal than 2 from U onto V. And what you do essentially is that you're going to do a model map where for polynomial-like mappings, you do a model map F such that you keep the dynamics, you restrict to F in U, okay? In the exterior of V, you are going to essentially put, you're going to use some Riemann maps and so, but you are going to put degree set to the power of V, okay? And in the annulus between U and V, you're going to interpolate. Okay, you're going to put some quasi-conformal map, which is going to be the interpolation. So that's essentially how you get to work with polynomial-like mappings. So what we want to do is the same. So I'm first going to assume I have this situation. I'm going to afterwards show that you can get actually this situation. So what we have is several curves. I have a curve beta in, 2 in, beta 2 out, which are mapped onto a curve beta 1 out, okay? This annular region here is mapped onto this annular region here with degree 6, okay? And we have this curve beta 2 out, which is mapped with degree 4 outside. We have this beta 1 out, which is also mapped with degree 4 outside. And what happens? So outside, essentially, I'm being mapped out. So I had this curve here, which is mapped here. I have a curve which is a little bit more outside, which is mapped outside. So essentially, in the exterior part, I have something like polynomial-like mapping, and I could do simply as polynomial-like mapping surgery. I could simply, outside, I can simply glue z to the power of 4. It's easy, it's usual surgery. So what happens inside? Inside the annulus, what I have, this curve beta 1 in is mapped with degree 2 onto this beta 1 in inside. This beta 1 in, which is inside, beta 2 in, is mapped outside itself. So now we have, before we had orientation preserving of some sort, now we are somehow orientation reversing. But we have this degree 2 here, okay? So somehow the exterior is mapped to the exterior with degree 4. The interior of this annulus is mapped to the exterior of this disk with degree 2. So somehow the idea is that we can actually do the same kind of surgery, and I'm going to put 1 over z squared in the interior. Okay, so the idea is the same. Essentially, you have to, I don't want to write the details because it's very similar to the polynomial-like mapping. So your model map F is going to be your RA squared in the annulus bounded by beta 2 in and beta 2 out. So you are going to have z to the power of 4 in the exterior of beta 1 out. And we are going to have interpolation in the green zone, in the green. Now, the next question is, actually, you are giving me a model map. Is this model map realizable? Can we have a holomorphic map which does realize these dynamics? You can here, for instance, use Shishikura principle. By construction, the points where the dynamics is, the map is quasi-conformal, well, any point will pass at most once through the region where the dynamics is, the map is quasi-conformal. So from the Shishikura principle, automatically you have that this map is realizable, that you are going to have a holomorphic map that that it's going to realize this model map F. Having said that, this is not a good idea to use, in this case, Shishikura principle, because what you want to add here, what's not in this figure, is symmetry. You need symmetry. Okay, so as I was telling before, we had a symmetry. Our map is symmetric with respect to third roots of the unity. Our map, in this case, this map here is going to be symmetric. Also, this McMullen map here is also symmetric with respect to third roots of the unity. And you want to prove that your model map is also symmetric with respect to third roots of the unity. So you can do this. The easy part is that z to the power of 4 is symmetric with respect to third root of the unity. That's easy. Our original model map, also is. It's more or less easy that the typical interpolations on annulus can be taken to be symmetric too. So your model map is symmetric. Once you get that your model map is symmetric, what you can also show is that the Beltrami coefficient is invariant with respect to pullback by a third root of the unity. From there, you get that the interpolation map is also invariant with respect to multiplication by third root of the unity. So you will get, I'm going to claim that the final holomorphic map that you will get will also be symmetric with respect to third root of the unity. To get this kind of arguments, you cannot pass through Shishikura principle. You really need to go through the Beltrami coefficient to justify properties about your integrating map. And the next part, okay, I'm going to erase this. Oops. So the next question is, okay, but you've told me that you want to reach here. I want to reach here. So what do we have? So we have a map such that our model map will satisfy the following. So at infinity, we've looked z to the power of 4. So we have that infinity is super attracting of local degree 4. Okay. Now, what else do we have? We have that at 0, we've placed a double pole. A double pole, so we have that infinity 0 is a double preimage of infinity. What else do we have? We have symmetry with respect to third roots of the unity. Okay, so which is the candidate I can have? So the only maps that satisfy all these properties are, I'm going to have something which has this form, set to the power of, set to the power of 4 plus b z plus lambda over z squared. So all maps which satisfy these upper properties have this form. The next question is, but I do not want at all B. So I do not want B at all, okay? But now our model map, I haven't talked since our map here has, since I am mapping 6 at this region here with degree 6 to a simple closed disk, means that you need 6 critical points. After the original map R has 3 critical points, 0 is a double preimage of infinity. What happens is that these 3 critical points after perturbation appear near infinity. Since you are 0 is mapped onto infinity with degree 2, these 3 critical points near infinity become 6 critical points near 0. These 6 critical points that appear near here, they are here, 1, 2, 3, 4, 5, 6. Okay, so we have 6 critical points which appear near 0. But R only has 3 critical points, which means that whenever we iterate these 6 critical points under R squared, they are mapped these 6 critical points, but only 3 critical values. Okay, it can be shown that they cannot be mapped, the 6 critical points cannot be mapped onto a single critical point, because then you would have problems with the degree. Okay, this our map here has degree 6. Our map has degree 6. Is the 6 critical points are mapped onto a single critical point, a critical value. This critical value has 12 preimages. So this would be a contradiction from the fact that our model map has degree 6. So actually, what happens is that 6 critical points are mapped to 3 critical values. And if you work a little bit with that, this implies that B is equal to 0. And we are done. So that's how, doing surgery, you can actually recover the McMullen family. But then I've tricked you a little bit in the following sense. How do you get these curves? It's not the difficult part of this construction is to actually get these curves, to actually get to know how are you going to get these dynamics. So in order to get these curves, you have to go and say, and to talk about these people I've been forgetting about all talk long, meaning the superattracting fixed points. I have superattracting fixed points, which are the roots of the unity. So I have here 1. What happens here? I have here 1. I have here chi, which is e to the 2 pi I thirds, and I have here chi squared. Okay, so I have these 3 roots of the unity. Another thing that I mentioned, it was written in a slide, but I didn't say it out loud, is that these maps only have 3 fixed points other than the roots of the unity. So what happens is that if you consider the Böttcher coordinates of this root, you can go and create an invariant curve under R0. This is the unperturbed map. This is R0. This is the unperturbed map. Okay, so what happens is that if I consider the external ray of angle 0, it can do something like that. If I consider the external ray of angle 1/2, which is also fixed, does something like that. And we repeat this by symmetry. So you have another external ray of angle 0, another external ray of angle 1/2, external ray of angle 0, external ray of angle 1/2. And that's an invariant curve. Okay, that's an invariant curve that, by the way, you can see here in the middle, 0 is here. Okay, so this is this invariant curve is separating 0 from infinity. And you can start from there. You can start from there, and you can start to build the invariant curves for R0. Okay, so with the first thing that you do, you have this curve. This curve is essentially going to be called gamma, and I can consider the preimages of this disk. If you consider the preimage of this black disk, the disk curved by gamma, I'm going to have this region D infinity, which is essentially consists of the curves of angle of external rays of angle 1/3 and 1/6, which are the external rays which are mapped to period angle 0 and 1/2 out inside, plus preimages in other connected components of the basin of attraction. That's outside, and what you get is the exterior of this blue curve, which is a preimage of this black curve I was drawing before, is mapped 2-to-1. So all this region here is mapped 2-to-1 onto this region here. And now you can do, but I've done this outside. I can do the same thing inside. So if you do the same thing inside, you get this region here in blue, in pallid blue, let's say, which has the rays of angle 5, 6, and 2/3, and which is also this one, this region here is mapped 2-to-1 onto the outside of the black disk. And this, you say, and you want to use these curves to somehow do a straightening like surgery. But if you want to do a straightening like surgery, these curves cannot touch. So the first thing that you have to do whenever you want to build the surgery is that if you see here the black region, I crop it a little bit near the attracting fixed points, the super attracting fixed points. So you simply go here near the attracting fixed point. You are going to go and you are going to replace this tip. You are going to replace this tip by some curve over an equipotential on the immediate basin of attraction of the super attracting fixed point. So you cut a little bit the curve, and you get something like this. Now you can take a preimage of this outside. If you take a preimage of this outside, you will get a crop version of this blue curve that we had before. This is a crop version of this curve outside, and this is I'm going to call this gamma 1. And I can keep doing this outside and inside, outside and inside. The outside of this blue curve has a preimage which is inside the black curve, which is this curve here in green. So this curve here in green is mapped with degree 2 to the blue curve, and the blue curve is mapped with degree 2 to the black curve. So in particular, for R², gamma 2 is mapped with degree 4 onto gamma 0. And this is, and somehow this curve, gamma 2 for R², for R², this curve is mapped here with degree 2. Okay, no, this is. So, and that's how that's the idea of how you are going to go and build the curves. Okay, so you are going to use the external rays from the basin, the vector coordinates of the super attracting fixed points to be able to do that. And whenever I was talking about lambda before, the set of parameters for which you can do the surgery is actually going to consist these external rays. You can continue them holomorphically. You can do a holomorphic motion of these sets, and so actually the set of points for which you can do the surgery, it's a dynamical characterization. It's the set of points for which you can continue these external rays, which essentially means that the critical points that come from infinity do not touch these external rays. So that's how you are able to do the surgery without going for A small enough. You go for the critical points do not do such and such thing. And that's how you are going to be able to still see a lot of the dynamics. So that's the idea of how you build the curve which is mapped out. The curve which is mapped out appears before surgery. Okay, and then the question is, where's the curve which is mapped in appears after surgery? What happens is that after surgery, infinity is after surgery we still have that 0. 0 is still mapped onto infinity with degree 2. But now infinity is mapped onto infinity 1 to 1. Okay? So what happens is that after surgery, you are putting a copy of everything near infinity. At infinity, you add a copy of everything. In particular, I had the curves gamma 0 and gamma 2 here. I had here gamma 0 and gamma 2, which had our prescribed dynamics. And what happens is that near infinity, there appears a curve gamma 0 prime and gamma 2 prime, which are mapped 1 to 1 onto gamma 0 and gamma 2. Okay, this is not the 1 to 1 I want, right? So with these curves, gamma 0 and gamma 2 prime appear, are the preimages of the curves I already draw, which appear near infinity and are mapped with degree 2. But now notice that 0 is mapped onto infinity with degree 2. So this what's going to happen, and I'm going to write this in a new slide. So I had this. I had here gamma 0 prime. I had gamma 2 prime, and I'm going to deform a lot the dynamics. So I have a neighborhood. So I have a neighborhood of 0, which is mapped 2 to 1 onto a neighborhood of infinity, and it's orientation reversing. So what's going to happen is that the exterior curve is going to have here a gamma 0 prime prime, which is mapped with degree 2 onto gamma 0 prime. And I'm going to have outside it, I'm going to have a gamma 0, gamma 2 prime prime, which is mapped with degree 2 also into gamma 2 prime. And this gamma 0 prime prime is what I was calling before gamma in 1, and this gamma 2 is beta in 2.
Sorry, Jordi, can I ask you to just back
sure.
up a moment? I'm slightly confused by your statement. You said the curve inside appears after surgery.
Yes.
But as I understood your surgery construction was you start with a situation where you have the outer.
Sorry,
the
it appears after singular perturbation, I meant. I meant under singular perturbation, sorry, my bad.
Okay, all right, thank you. So your outside curves come from the original map that you have in the middle, and they persist in some region in parameter space.
Exactly.
And then once you add the singular perturbation, you also have the inner curves, which are okay. Thank you.
Okay, sorry, yes, I was going a bit too fast. So yes, and if you have any questions, please do not hesitate to ask me. So that's these regions appear. These curves, these four curves I'm drawing here explicitly appear after perturbation. So in these curves, in particular, are the curves beta 1 in and beta 2 in, which are mapped outside, which are mapped to the complement after singular perturbation. Okay, and this is somehow the idea. This is more or less the idea of how you get this McMullen-like situation. So it's instead of polynomial-like, we have here a McMullen-like situation here. Okay, and once you do the surgery, another property is that the final corollary. I have like 3 minutes maybe. Okay, and then we have this situation where we have the final corollary. Actually, we have much more than that, but we have final corollary, which is if modulus of A is small enough, then the Julia set is connected and contains an invariant Cantor set of quasicircles. So yes, let's just recapitulate. So what does this mean? So remember that our construction is done for RA squared, not for RA. So what happens that if modulus of A is small enough, what you prove is that actually you are in the situation for the Cantor set of quasicircles. The Cantor set of quasicircle situations in McMullen case means that you have here the trapdoor, you have the trapdoor, which is the preimage of infinity, and you will have an annulus, a straight, well, almost straight annulus, which contains the 6 critical points, 1, 2, 3, 4, 5, 6, which is mapped with degree 6 to 1 in here. So you actually have to work a little bit here and show that if modulus of A is small enough, you will have a straight annulus, which is mapped inside of a 2-component and this straight annulus contains the 6 critical points, and you have to prove that this straight annulus is the Fatu component is not the same for everybody. So it's actually a Julia set separating this annulus from 0. And with this, you can show this for a modulus of A small enough, but somehow you get a Cantor set of quasicircles for RA squared. So this is for RA squared, this is mapped here onto itself, okay? But what happens actually is that if I consider RA, what I'm going to get is that this Cantor set of quasicircles is mapped into another Cantor set of quasicircles which surrounds the origin, okay? Which surrounds infinity and separates infinity from the origin, and which is also mapped onto the original one. So what's going to happen in the end, actually the statement could well say that your map has a period 2 Cantor set of quasicircles, which is invariant inside the dynamics. But if you take these 2 Cantor sets of quasicircles together, they form a set of Cantor set of quasicircles. So you can say that you have a Cantor set of quasicircles, which is invariant. And also you had this, we had this, this situation here, all these decorations here. I want to mention where they come from. So you have inside the annulus here, inside this annulus, you see these things like this, and what are these decorations? You can see, you can somehow, if you go to the original map, if you go to here, sorry. If you go to here, so what you're watching inside the annulus, it's simply coverings of the original Julia set. So you're going to have this original Julia set making everything connected. The structure of the Julia set, if in particular for the Cantor set of quasicircle case, you can show that you can actually follow the whole copy of this Julia set. This Julia set is still there. For the Cantor set of quasicircle says you can actually do a holomorphic motion of this full Julia set. It's all this structure is there, so that's why you can do that's what you can observe in that Julia in that Cantor set of quasicircles in the bottom. So that's more or less what I wanted to explain. So thank you very much. Thank you. Thanks for your attention.
Thank you very much, Jordi. Are there any questions?
So you map lambda, I think you called it, between the parameter spaces. So is this a homeomorphism between the set of, the bifurcation locus of the corresponding singular perturbation theory and the corresponding subset, the correct subset in the bifurcation locus of your family?
Look like a homomorphism, but we're still working on proving that much.
So this would be analog of the Jordi-Hubbard.
So that's your
little Mandelbrot copies theorem, right?
Yeah, and that's what we are working on. So in the beginning, we wanted to show this is actually feasible, but going these parts, you have to be very careful because even we have the same problems with the continuity of the surgery that you get for the Jordi-Hubbard. So it gets tricky at some moments. So everything seems to work well. We have certain regions where clearly it seems to work very well, but we still have to that part is a work in progress.
Okay, thank you very much.
Any further questions? If there are any questions online, please unmute yourself and feel free to ask. If not, let's thank Jordi again. And then we have a coffee break until 11:55 because we're a bit late. Sounds good.
Sorry, I don't know if I.
We resume 5 minutes later than planned because we are getting delayed. So we meet again at 11:25 time.
Like I started.
No, you started.
Okay, I finished like 5 minutes.
I'll wait to this off.